All right, welcome future engineers and technicians. Today, we're going to dive into two absolute foundational processes in plastics manufacturing, compression and transfer molding. We're going to break these down so that by the end of this, you'll be able to identify them, classify the products they make, and really understand how they shape so much of the world around us. Let's get into it. So, to get started, here's a little puzzle to get your gears turning. Think about it. A waffle maker, a big car body panel, and a tiny electrical switch. They seem completely random, right? But what could they possibly have in common? And the answer is, it's all about how they're made. Yep, all of them rely on some really powerful molding techniques. And guess what? These are the exact techniques you're about to get a handle on. Seriously? Understanding this stuff is your ticket to really getting the world of plastics engineering. So, let's jump right in. Okay, first up, Section 1, compression molding. You can think of this as the OG, the original process. It's one of the oldest methods in the playbook, a true workhorse of the industry. Known for being super reliable, especially when you're working with those tough, heat-resistant plastics called thermosets.
So what is it really? Well, at its core, the idea is incredibly simple. You take a pre-measured amount of your material, we call that the charge, you place it into a heated mold, and then you just squeeze it. A lot. That combination of intense heat and immense pressure forces the material to fill every single nook and cranny of the mold, creating a super strong and durable part.
You know, the absolute best way to remember this process is to think about making waffles. I'm serious. You pour the batter, which is your material charge, into the hot waffle iron. You close the lid, which applies heat and pressure. It's the exact same principle, just, with industrial-grade machinery and materials.
Let's walk through the cycle. It breaks down into 4 simple stages. First, you place the charge into the lower half of the mold. Step 2, the upper mold half comes down, closes everything up, and applies pressure. Now for the magic part. Step 3, the cure. You maintain that heat and pressure, and it triggers a chemical reaction called cross-linking. This locks the material's molecules into place, making it permanently hard. And finally, Step 4, the mold opens, and the finished part is ejected. Simple as that.
So now that we have the process down, let's pop the hood and look at the key ingredients. Section 2 is all about the materials you're putting into the mold and the different types of molds themselves. This is where your decisions as a technician or an engineer really start to count.
When we talk about materials here, we're mostly dealing with thermosetting resins. And the name gives you a huge clue. Once you heat them and they set, that's it. It's a permanent chemical change. It's kind of like baking a cake. You can't unbake it. Things like phenolics and melamines are super popular because they're incredibly strong and heat-resistant. For larger structural parts, you'll often run into composites like sheet molding compound, or SMC, and bulk molding compound, BMC.
Now, for all you future technicians, this is critical. You gotta know your molds. First up is the open flash mold. It's a bit forgiving. You can overload it slightly, but that extra material squeezes out as waste, which we call flash. Then you have the fully positive mold. This one is a total perfectionist. The material charge has to be precise. No extra room means you get a very clean part with almost no waste. And you guessed it, the semi-positive mold is that best of both worlds option, a nice compromise between the two.
Okay, so compression molding is fantastic for strong, simple parts. But what if your part isn't simple? What if you need to create something with lots of intricate details, or maybe embed some delicate metal inserts inside? Well, that's where our next process, transfer molding, comes into the picture. It's a very clever variation.
Think of transfer molding as the clever cousin of compression molding. It uses the same basic principles of heat and pressure, but it adds an ingenious twist to get around some of those limitations. And the whole thing hinges on one key difference: where the plastic starts its journey.
And here it is. This is the single most important difference to remember. In compression molding, you put the material inside an open mold. With transfer molding, the mold is already closed, and you load the material outside the mold in a separate chamber, and then transfer it in. It seems like a small change, but believe me, it makes a world of difference.
So why is this so important? Well, let's look at the cycle. First, you put the charge into that separate transfer pot. Then, you heat the pot to get the material nice and soft, almost like a liquid. Next, the transfer. A plunger forces that soft material through channels and into the closed mold. Because it flows in so gently, it's perfect for creating complex parts with fine details. And it won't disturb or damage any delicate inserts like wires that you've put in the mold. Then, it's the same old story: cure and eject.
Okay, so here's the million-dollar question for you as a future engineer. Which process do you choose? Your job is to weigh the pros and cons of each method to find the absolute perfect fit for whatever you're trying to make. So let's break it down and put them head to head.
This table is pretty much your cheat sheet. Look, if part complexity is low, compression molding is your go-to. It usually has less material waste, which is great for your bottom line. But if you're dealing with really intricate shapes or you need to mold around metal inserts, transfer molding is the undisputed champion. The trade-off is typically higher waste from material left in the pot and runners. It's always going to be a balance of complexity, waste, and cycle time.
And if we just look at intricate parts, well, this chart says it all. It's not even a contest, right? Compression molding is low on the suitability scale. Transfer molding, it's way up there. That ability to gently flow material into a closed mold gives it a massive advantage for creating those fine details.
All right, that's enough theory. Let's bring this all back down to earth, to the real world. We'll look at some everyday products made with these processes, and then we're going to tackle one of the biggest challenges you'll face on the job: product defects.
I can almost guarantee you've used a compression molded product today. That sturdy handle on a cooking pot, the electrical socket on your wall, those tough melamine plates, all classic examples of compression molding's strength and durability at work in the real world.
Now, when it comes to high-performance, high-stakes applications, transfer molding is the star of the show. We're talking aerospace components, parts for wind turbines, high-tech helmets, and especially things like electrical components where you have delicate wires embedded right inside the plastic. In these cases, precision is absolutely non-negotiable. Okay, let's talk about one of the most common problems you're going to face as a technician: defects. And the number one culprit is usually flash. See that little thin web of extra plastic that squeezes out where the two halves of the mold meet? That's flash. It's annoying, it's wasteful, and you've got to deal with it.
But don't worry, we've got ways to fight back against flash. Two of the most common methods are tumbling and blasting. Tumbling is pretty low-tech. You literally just tumble the parts against each other in a big basket, and that brittle flash just breaks right off. Blasting is a bit more sophisticated. You shoot a stream of fine particles, and this is cool, sometimes it's crushed walnut shells, at the part, and it abrades the flash away without hurting the main part. Phew! Okay, we have covered a lot of ground, so let's pause and just boil it all down. Section 6 is all about your key takeaways. These are the absolute essential concepts that you need to lock in.
Here are the 4 big things to remember. Number 1, compression molding is your waffle maker, great for strong, simple thermoset parts. 2, transfer molding is the clever variation, transferring material into a closed mold, which makes it perfect for complex parts. 3, the biggest difference is where you load the material, inside versus outside the mold. And 4, your choice always comes down to a trade-off between part complexity, material waste, and cycle time.
And now, the torch gets passed to you. You have the foundational knowledge. You know the how. The next step is to take this and apply it to innovate and solve real-world challenges. So, I'll leave you with this question to think about. To design that next generation of lightweight, high-strength parts, which process would you choose and why? The possibilities are all yours.